So AI is moving incredibly fast, right? Beyond just text. Now it's images, audio, all sorts of things. But think about this. One single AI, not just seeing a picture, but actually creating one in the same system.
Yeah, that's the big idea. The elegance of it is pretty compelling.
Exactly. That's this whole area of unified multimodal models. And well, GPT-4o from OpenAI really threw a spotlight on it recently.
It really did. Having one system handle both understanding and generation, I mean, it just feels more efficient, potentially much more powerful. Think about the interactions that could enable.
Totally. So that's what we're diving into today, this cutting-edge research looking at exactly that. AI models that can understand images and generate them, all unified.
And we're looking at a really interesting paper for this, BLIP3O, a family of fully open, unified, multimodal models architecture, training, and data set. It really gets into the nuts and bolts of the best ways to build and train these kinds of systems, especially now including image generation.
Okay, BLIP3O. Let's unpack that. What's the core problem they're tackling here?
Well, fundamentally, they're trying to figure out the best way to combine two powerful types of AI. You've got autoregressive models. They predict things step by step, kind of like writing a sentence.
Right.
And then diffusion models, which are amazing at generating really high quality stuff like images. The question is, how do you make these two work together smoothly in one framework?
Okay, and it sounds like they've got a specific new approach. What's the key innovation with BLIP3O?
Yeah, the big thing is how they handle the image generation part. So instead of the maybe more traditional route using VAEs, variational autoencoders, to represent the image, they've developed this method using something called a diffusion transformer. And its job is to generate these really meaning-rich CLIP image features.
Ah, CLIP features. Those are the ones that capture the meaning of an image, the semantics, in a way that lines up well with text descriptions, right?
Exactly. CLIP is brilliant at getting the essence. So the idea is, by generating these high-level CLIP features using diffusion, you aim for better image relevance and quality, maybe more efficiently than focusing just on pixels like VAEs often do.
So focusing on meaning first, then letting diffusion paint the picture based on that meaning.
Pretty much, yeah. It's a shift in focus from low-level pixels to high-level semantics for the generation target.
And the fully open part in the title, that sounds pretty significant for the research community.
Oh, it's huge. They didn't just build these models. They released everything. The code, the model weights, the data sets they curated.
Yeah.
It's all out there,
Wow.
which means anyone can verify it, build on it, push the field forward faster. It's a really valuable contribution.
Okay, great. So before we dive deep into the how, let's just step back. Why is everyone so excited about this unified approach? Why build models that can both see and imagine?
Well, there are a few really compelling reasons. First, it just massively improves reasoning and instruction following.
How?
When you bake image generation into the language model, it gets way better at understanding prompts that need visual knowledge, world knowledge. Like if you ask for an animal with a long nose, a unified model doesn't just know facts about elephants, it can visualize it, connect the concept, and generate the image.
Ah, I see. It connects the language understanding directly to a generative capability.
Precisely. And the insight here is kind of splitting the job. The language part figures out what to generate semantically, and the diffusion part acts like the artist, rendering that semantic idea into pixels.
Okay, that makes a lot of sense. Better reasoning. What else?
Second big thing is in-context learning, because the model can generate something and then use that generation as context for the next step.
Right.
It opens up cool possibilities. Like you could edit an image iteratively just by talking to it,
Right.
or have a visual dialogue where it responds with images, or even step through visual reasoning problems.
So it can build on its own work, essentially. That sounds powerful.
It is. It allows for much more dynamic and extended interactions.
And the third main motivation.
That's the sort of grand vision, moving towards multimodal artificial general intelligence, or AGI.
The big one.
Yeah. I mean, future AI needs to handle all sorts of information, seamlessly perceive, interpret, create, just like we do. Unified models are seen as a crucial step on that path.
It's like giving AI eyes and an imagination, not just a library card.
That's a good way to put it. It's about a richer, more grounded interaction with the world.
Okay, the why is clear. Now the how. You mentioned combining autoregressive and diffusion models, maybe like GPT-4o does. How does that hybrid setup work in practice?
Right. So the speculation around GPT-4o suggests this flow. Text tokens go in, the autoregressive part processes them, its output feeds a diffusion model, and that generates the image pixels.
Okay.
And this paper basically takes that idea and asks two really fundamental design questions that arise from it.
Which are, Brett?
First, What's the best target for the model to generate? Should it be aiming for those VAE features, which are closer to the pixels, or should it aim for CLIP features, which capture that higher level meaning?
VAE versus CLAP for the target representation. Got it. And the second question.
Second, how do you best align the output of that first autoregressive stage with whichever target you choose? Do you use a simpler method like mean squared error, MSE loss, or do you use a more complex diffusion-based approach like flow matching?
Okay, these seem like core architectural choices. Let's tackle the first one representing the image. VAEs versus CLIP with a diffusion decoder. What are the trade-offs?
So VAEs, variational autoencoders, they're pretty standard. They compress an image into this hidden continuous space, and then a decoder part reconstructs it. They're generally good at capturing fine details, pixel-level stuff, plus you can often find pre-trained ones ready to go.
The established method, then.
Pretty much. But the alternative they explored is using a CLIP encoder, which gets you those semantic features we talked about, and then pairing it with a diffusion decoder to reconstruct the image from those features. The EMU2 project explored this kind of idea before.
And the advantage of the CLIP approach?
It's mainly about the representation itself. CLIP can often summarize an image into a fixed number of vectors, say 64, like in the paper, no matter the image size, and these vectors are packed with meaning.
More efficient, maybe.
Potentially, yeah. Better compression, especially compared to VAEs, which might need longer sequences for high-res images. So the takeaway for you is this focus on meaning with CLIP, and then potentially more creative generation using diffusion methods like flow matching.
Interesting. So CLIP gives a compact, meaningful summary. Okay, now the second question, modeling that representation. MSE versus flow matching. What's the difference there?
So the autoregressive model spits out some visual features based on the prompt. You need to train it so these predicted features match the real target features, VAE or CLIP. MSE is the straightforward way.
Just measure the difference.
Yeah, basically calculate the average squared difference. Simple, common, but.
There's always a but.
Right. The but is that MSE tends to push the model towards predicting the average possible output. This makes the generated features kind of deterministic. Same prompt, very similar features, very similar images each time. Less diversity.
Ah, okay. Good for consistency, maybe, but not if you want variety.
Exactly. And that's where flow matching comes in. It's a diffusion technique. Instead of predicting one specific output, it learns to model the whole distribution of possible outputs.
How does that work, roughly?
Think of it like learning a smooth path from noise or a blurry image to the clean target representation. It learns the velocity needed to move along that path. Because it models the whole probability space, you can sample from it stochastically, leading to more diverse outputs.
Sounds more involved than MSE.
It is. It usually requires a more complex model, like the diffusion transformer they used. But they found that giving this part more capacity really paid off in performance. The complexity was worth it.
Okay, so we've got VAE versus CLIP for the what, and MSE versus floor matching for the how. The paper-tested combinations, what did they find?
Yep. They looked at CLIP plus MSE, CLIP plus flow matching, and VAE plus flow matching. They checked how well the generated images matched the prompt using metrics like Geneval and DPG Bench, and also looked at visual quality using FID.
And the winner was?
Well, CLIP combined with flow matching consistently did best on prompt alignment. So using those semantic CLIP features and modeling them with flow matching really seems to help the AI generate what you actually asked for.
That seems pretty important.
Definitely. Now, interestingly, the VAE with flow matching sometimes got better FID scores, which usually suggests better aesthetic quality.
But you mentioned FID isn't perfect.
Yeah, the paper notes FID can be a bit unreliable. Even top models like GPT-4o didn't ace their FID test, despite making great images, so you need multiple metrics, and ideally human eyes. But overall, the evidence pointed strongly towards CLIP plus flow matching being the most effective combo.
Got it. So key findings. Learning semantic features, CLIP, seems better for the autoregressive part than pixel-level ones, VAE. And flow matching beats MSE for capturing the image distribution, leading to better diversity and quality. Those are their findings 1 and 2, right?
Exactly, and those findings really shaped how they designed BLIP3.
Makes sense. So building on that, how do they actually train this unified model? The paper mentions joint versus sequential training. What's the difference?
No, joint training is like teaching everything at once, mixing up image understanding tasks and image generation tasks during training. Multitask learning, basically.
Learn both skills together.
Right. Sequential training is a two-step process. First, you train the model really well on image understanding, get that part solid. Then you often freeze that understanding part and then train the image generation module.
Master one, then add the other. Any pros and cons?
Joint training could have synergy, where learning one helps the other. But getting the data mix right, how much understanding versus generation data can be tricky and might need huge data sets. Sequential training gives you more control. You lock in the understanding skills, then dedicate all the resources in stage 2 just to perfecting generation without worrying about degrading the understanding part.
More focused, maybe safer?
Yeah, that flexibility and safety seemed appealing. So for BLIP3, they went with sequential training.
Okay, that makes sense. So let's get into BLIP3 itself. They made an 8 billion and a 4 billion parameter version. How did they build them, especially with the open source goal?
Right, so instead of starting from absolute zero, they smartly built upon existing strong open source understanding models, specifically the Qwen 2.5 VL model.
Leveraging what's already out there.
Exactly. For the 4B model, they essentially added their generation module onto Qwen 2.5 VL. For the bigger AB model, they took the Qwen 2.5 VL7B instruct model, froze its main understanding backbone, and then trained their diffusion transformer for generation on top. That added about 1.4 billion new trainable parameters just for generation.
So it's like giving these powerful seeing models an imagining module.
Precisely. A very efficient way to get to state-of-the-art, especially for the open release.
And this diffusion transformer module, what's special about its architecture?
They based it on Lumina Next, which itself comes from NextD. These are architectures designed for scaling up generation. Key bits include things like 3D rotary position embedding.
Sounds complicated.
Think of it as helping the model understand spatial relationships and how things change over the generation time. They also use standard but effective techniques like RMS norm for stability and grouped query attention to make the attention mechanism more efficient. Pretty cutting-edge stuff for transformers.
Okay, sounds like a solid foundation.
Yeah.
Now, the training recipe. How did they teach these models? You mentioned 2 stages.
Right. Stage 1 was pre-training for generation. For the big 8B model, they used a mix of public data CC12M, SA1B, JourneyDB, about 25 million images, plus another 30 million internal images. The crucial part, they paired all these images with really detailed captions generated by Qwen 2.5 VL7B instruct, like 120 words on average.
Wow, that's descriptive.
Very. But they also mixed in about 10% shorter captions, around 20 words, to make sure it could handle different prompt lengths.
And the fully open 4B model.
That used just the 25 million public images, but with the same detailed and shorter caption sets. And importantly, they've released both caption datasets, 25 million detailed, 3 million short. A huge asset for the community.
That really is fantastic. Okay, so that's pre-training. What about stage 2, the instruction tuning? Why was that needed?
Well, after pre-training, they noticed the model still struggled with some specific things. Generating believable human gestures, common objects like specific fruits, recognizable landmarks, even putting simple text in an image clearly.
A tricky detail.
Exactly. So instruction tuning was designed to specifically target and fix these weaknesses.
How did you do that?
They used GPT-4o. For each problem area, gestures, objects, landmarks, text, they prompted GPT-4o to generate about 10,000 targeted prompt image pairs.
Using one powerful AI to teach another.
Kind of, yeah. They also mixed in data from JourneyDB and BLIP3 to boost general visual aesthetics. This resulted in a specialized, high-quality tuning dataset of about 60,000 examples. And guess what?
They released it too.
They released that too.
Incredible. Did they learn anything interesting from this stage?
Yes. Finding 3 in the paper. Their model adapted really quickly to the GPT-4o style images and surprisingly seemed to learn more effectively from these AI-generated images for certain aspects than from real photos.
Huh. That is interesting. Okay, so after all that building and training, the results. How did BLIP3 actually stack up? Let's start with understanding.
On the understanding side, they tested it on a whole battery of benchmarks, VQAV2, MMBench, MMMU, you name it. The 8B BLIP3 model basically achieved state-of-the-art results across most of them, beating many existing models.
Very strong on understanding then. And image generation.
For generation, they used metrics like Geneval and DPG Bench for prompt alignment and WISE for world knowledge reasoning. BLIP308B got really competitive scores on Geneval and WISE. Its DPG Bench score was a bit lower than some, but they noted that metric, especially when evaluated by another AI model, can be a bit unreliable.
Right, the numbers don't always tell the full story. Did they do any human checks?
They did, and this is crucial. They pitted their 8B model against another strong open model, Janus Pro 7B. Humans looked at images generated for the same prompts from DPG Bench and rated visual quality and how well they matched the prompt. BLIP3 won out significantly on both counts, according to the human judges. Even though Janus Pro actually had a slightly better automated DPG Bench score, it really shows BLIP3O's generation resonates well with people.
The human evil is super important, really validates their approach. Okay, so looking ahead, where do they plan to take this work?
They mentioned wanting to extend it to more interactive stuff, things like complex image editing via text, multi-turn visual conversations back and forth with images, and maybe even generating interleaved text and images. Their immediate next step seems to be improving basic image reconstruction using their unified framework.
Logical next steps. So let's wrap this up. What are the main things we should take away from this deep dive into BLIP3O?
I think the big picture is that BLIP3O is a really significant step for unified multimodal AI. It shows you can get top-tier performance in both understanding and generation in one model. And the key seems to be these architectural choices, using semantic CLIP features as the target and employing flow matching to model them effectively, combined with that careful sequential training.
Yeah, those specific findings about CLIP and flow matching feel like really valuable insights for anyone working in this area.
Definitely. And honestly, their commitment to open sourcing everything, the models, code, weights, and those massive caption data sets, that's just a massive boost for the whole research community. It makes it so much easier for others to build on this.
Absolutely lowers the barrier to entry.
Yeah.
So as a final thought for you listening, think about what truly unified AI like this enables. Systems that don't just process information, but can seamlessly create across modalities, images, text, the more down the line. How could that change how we interact with tech, how we create things? It's definitely something to chew on. We'll drop links to the BLIP3O paper and project in the show notes if you want to explore it further yourself.